This is how ChatGPT imagine Galileo. He's programming in Python, so Python must be good. He has a smartphone, so it's also, I don't know what the statue behind is doing, but anyway, so that's how Galileo looks like now today. And the idea is that, I'll come back to those two slides now. So the idea is that you know the experiments, and you know that you've studied in first year of physics, since I guess you're all physicists, almost all physicists. And you know that it doesn't depend on the mass. But Galileo didn't know that and decided to check if that's the case or not. Does it depend on what depends exactly? Okay. And so the first thing that you can do is, you start doing measurements. Now, those numbers, I created them with the questions because I could not go to the Tower of Pisa and measure that. But basically what I did, I generated random masses. I took random times and I calculated the distance traveled. Okay. Imagine that you do that from the Tower of Pisa and you measure them. Okay. You have a data set. So Galileo did all the experiments now, and now thought, okay, you know what? So I have no idea how the mass and the time and the distance traveled are related. So I'll use machine learning because I can throw data at it and it will do its magic. So you can build an actually model that predicts the distance traveled quite well. So actually really well. Okay, so this is what you see here is like the predicted versus expected. And since they're all on the diagonal, it means they're the same. So the model works really well. So, okay, I have a black box that can predict the travel distance. Now I want to do some science with it. Okay, so what you can do is you can start asking, for example, you have two features, you have the mass and the time, right? And you can ask, okay, well, what feature has the model used? And if you ask the model, you'll see that, for example, the mass is not used for the prediction and only the time is used, basically, okay? So you can actually, at this point, you can make an hypothesis, right? Saying that, okay, the mass, it doesn't seem to be relevant because machine learning is able to predict the distance without using the mass, okay? So machine learning has somehow helped us in generating an hypothesis, right? But that's just an hypothesis that needs to be, of course, then verified with further experiments and so on, as in any scientific endeavor. But it's basically, it helped us generating an hypothesis. Now you can go a step further and then saying, okay, you know what? You can use, and I'll talk about that, what's called symbolic regression. That's also a machine learning approach that allows you to search the space of all possible equations that exist to describe some relationship. And if you look at, you let it look at the data and you let it look at all the possible equations that might describe the data, and you end up exactly with 1/2 GT squared for the distance traveled, okay? So basically, Galileo could say, okay, I think I can say my hypothesis seems verified. That doesn't depend on the mass. And I know that there's a square dependence from the time. And you can even get the value of G if you're interested. This is an approximation of 981. But still, you can get quite some information that you might want to verify further, okay? So maybe that would have made Galileo maybe life easier. Maybe with the church could have been difficult anyway. But, oops, sorry. But basically, you can do lots of things that allows you to generate an hypothesis and study things, okay? But what I would like to point out is that what's important to note is that it's still embedded in a kind of a scientific approach where you have an hypothesis you're trying to understand, and then you go back and see, for example, okay, this formula seems the right one, so which theory would describe that? But it would allow you to make more educated guesses than simply, so just trying random things. So I will explain a bit that, but maybe just to avoid confusion, symbolic regression is not fitting the data with the formula. So you're not giving a formula to the system, you're asking the system to find the best formula that approximates and the simplest one. So it's actually a bit complicated. It's based on genetic algorithms, but the results are really cool. You can use it also with in multidimensional and so on. Okay. So one of the points that I think is really, really important is that I review quite a few papers, and most of them fail really to make kind of a scientific, let's say their scientific value is really limited. Okay. And one of the reasons is that, and I call it pseudoscience because it's really like they're very fancy and it seems they do lots of things. But at the end, there is really no scientific question that is answered. Okay. Because you always have like something that happens always, and I see it also in many like PhD projects, for example, is that you get the data set from someone and someone asks you, oh, look what you can do with the data set. And then you go and then you try some algorithms and you see what you can get out of it. And then you classify things and you cluster things and you do things. But I think that one should always start with a research question and saying, okay, what I want to do? What is the problem I'm trying to solve? And then depending on the problem you're trying to solve, you can decide what algorithms, what data, what do I need? Okay. And I think that if you use this approach, you'll start seeing like machine learning as it's an incredible tool, but like if you know a bit about the tools we were discussing also with Lorenzo about just clustering today, so how to use it to solve your question. So, right, and then basically, yesterday I was talking with my wife, and my wife said, but how do you define scientific machine learning? And I said, oh, scientific machine learning is what you use for science. And she says, so it's everything is scientific machine learning, depending on its use only. And it's actually true, but there are some techniques, some methods, some algorithms that are only relevant when you're doing science. So, for example, if you are trying to develop something to unlock the iPhone with the face, you really don't care. I mean, it's an engineering problem. So as long as it works well enough, nobody cares. It's like Google Maps, right? Nobody asks, okay, give me some metrics. So how accurate it is? You simply follow it because it works kind of 90% of the way. This is more an engineering problem. You try to solve the problem versus like you try to understand something. So that's a lot more complicated. Okay? And this is why I like this comparison. And I think that I like more like the science part than the engineering part. We were also discussing with Lorenzo this morning, like what you like. And one of the problems why scientific machine learning is difficult or less known is that it's coming from the engineering side. Okay? So many questions, for example, I'll talk about uncertainty quantification in machine learning because you want to know, for example, in physics you have errors and measurement errors and so on. And it's in engineering is kind of less relevant, right? As long as it works, it's kind of okay. You don't measure, like if you're building a system for Tesla to drive and to stay on the road, you don't measure exactly an average distance in millimeters from the road. You kind of say, okay, how many accidents we had this year? So 5, okay, it's good enough, right? While in science, you want to understand things. Okay, so, and this is when you think this way, you should always like see machine learning as a tool and not just as the goal. So saying, okay, let's cluster images of galaxies, nice but why, right? And so on. Okay. So just to give you an example, so I don't know, I'm pretty sure you have seen that the Nobel Prize in chemistry has been given to the CEO of Google DeepMind and other people, but basically well, we can discuss how much he really did in this area, or how much the researchers did. That's a different discussion. But basically, it was for models, deep learning models that are able to predict how proteins fall from the amino acid sequences. Okay, and that I would argue is not really science; it's engineering. There was no understanding why this is happening. Right? It's simply a tool, an incredible tool that solves a 50-year-old problem, but it's still a tool. Okay, so we can argue about how much this is science, but they got the Nobel Prize, and there was another Nobel Prize in physics. I'm sure you have seen it. That was given to another person that has done lots of work in machine learning. Lots of discussion about if it's really physics or not. But that's a different slide. Okay, so and basically, you know better than me that you have like an hypothesis, you design experiments, you perform the experiments, and then you verify, or better, you disprove, you try to disprove the hypothesis because an hypothesis cannot be verified. So if you like philosophy of science, then we can discuss that. But basically, what I'm trying to say is that when you follow this kind of blueprint, you have to think about experiments in machine learning exactly as you would do in a lab. So you have to sit down and think, okay, how can I design numerical experiment that actually helps me formulating an hypothesis? Okay. So if you think about the example of Galileo and the mass, you could think about, okay, I have to build the model, and then the model will, and then I do feature selection, and then I can get some information, and then if I have this information, I'll do maybe other experiments or I'll do something like that. So you have really to think, you have to design experiments, machine learning, what I call machine learning experiments. So what you do on a computer are really experiments like in a lab. And so they should be treated exactly the same way. So for example, what you should do is, and I tell all the students, you should always keep, for example, track of all the experiments, all the tests that you do. You should document them with the date, with what you found out. Because one thing that, for example, people do is that they change the code manually and change that, and then go back and change some parameters and run it again, and you go back and change some parameters and you go back, and after a while you have no idea anymore how you got the first results in the first place and things like that, right? While in the lab, if you've done experimental physics, you sit down, you have the lab, right? Notebook, you write the date and you write everything, and then it's and you should do the same here. So when you, for example, if you work with Jupyter notebooks, you should really have like Jupyter notebooks with all the tests, one after the other. The notebooks should run without errors, without manual intervention, so that you can always reproduce what you're trying to do. Okay? So also reproducibility is a topic that we can discuss about. I'm not talking about that, but it's also something that you should keep in mind that you're doing experiments in science, so everything should be reproducible and so on. Okay. So for example, engineering application of machine learning that in my opinion doesn't really add much to science are things like classification of observations just for the sake of it. And I think that everyone, probably me included, is guilty of like publishing things just because it was a hype and everyone was using it. And so you wanted to show that it's possible, but at the end, you really did not understand much more about nature before that. And then you compare model types, and you've seen, especially for example in medicine, you have like hundreds of papers of like they take a data set and then they try to predict something. They have like 82% of accuracy, and they compare models, and that's a paper. But basically, nice, but you show that machine learning can kind of find relationship between variables, and you know that, but that's actually the only really contribution actually. And then, for example, what also people have seen, like papers of people using machine learning on data set with 50 points. And so and also the value there, it's the statistical kind of analysis you need, it's also very often missing. So just to so in my opinion, a very good scientifically relevant paper should always follow this kind of and this is kind of how all scientific papers works, but in machine learning, people kind of forget them for some reason. Maybe they're excited about machine learning, or I don't know. But so if I see this kind of approach where you have like a scientific question to start with, then it starts to become really interesting. Okay? If I see that the machine learning is kind of the goal, unless you're developing a new algorithm and you're publishing on a computer science journal, it's probably not very relevant for science, but as maybe a provocative kind of idea or an opinion that I have. So what I want to do today is I want just to show you a few things that exist in scientific machine learning. Maybe you find something that is useful. We had discussion this week. We had already like ideas about things that we can do. So I'll try to show you a few things that I hope that maybe you'll find interesting in your work. There are so many things that you can actually look at. One big one that I'm not talking about is feature selection in physics. For example, there is a huge question, open question, for example, how you select the spectral bandwidth from spectra instead of selecting like single pixels, because machine learning is using like single pixel as input. And so how you select really spectral bands that are actually, because they are, the signal at close wavelengths is correlated. So it's kind of how you do things like that. There are lots of things that, especially maybe for people working in astrophysics, is relevant. Okay, so I said that like 2,000 times, so let's skip that. So uncertainty is one big big area of study in scientific machine learning, because you want to be able, the classical approach is that we were actually also discussing with Tatiana, is that you train a model on a certain data set and you want to predict something, right? Maybe it's a regression task, maybe you want to classify something. And then you want to apply maybe to a much larger data set where you don't have labels. And the question is, and this is why, for example, when I talk with astrophysicists, most people say they don't trust machine learning, is that you cannot give any kind of error of like, what is that? I mean, yeah, you can give like, like a mean absolute error on your data set, but really like, what kind of error can I expect when I use it on you? And, when you use on 200 million data points, what should I expect? Okay. And so there is an entire field in scientific machine learning that is called uncertainty quantification. And that gives you kind of lots of information about or methods to try to estimate how good the model can be. How for example, I'll show you a few examples. How, for example, error propagates and things like that. It's actually a bit complicated, and this is there are few slides with, formula. I mean, you're a physicist, I'm sure you're not afraid of formula, but I'll try to keep like the technical things at the minimum. And basically, uncertainty quantification, it's basically based always when you're working with model that gives you the probability, or let's say a number that you would like to interpret as a probability of an observation of being of a class, right? So what happens is that you can imagine the classical example is you have like, maybe dogs, right? Images and cats. Sorry for the stupid example. And when you have an image, your model will tell you that it will give you two numbers, maybe it's 0.85 and 0.15. So something that sums to 1, right? And then what you do is you assign the class by choosing the bigger one. And you would like to, so you build models in a way that the sum here is equal to 1, meaning that you would like to interpret that as a probability, right? Because if it sums to 1, it's a probability, you would like that. The problem is that if you want to interpret that in this way, what happens is that what if between all the dogs, you get only 40% right? So what does this 85 mean? It's not the probability of getting a dog right. Something else that is, there's no idea, right? And so there are like methods where you can actually, for example, define the average confidence. So you might say, oh, you know what? Between all the dogs, if I do an average of all these numbers, right, that you have, maybe you get, I don't know, 0.79. Okay, so you have like kind of what's called an average confidence of the model for dogs. 79. But if the accuracy for dogs is 45%, it really doesn't make much sense. Or at least you cannot interpret it really as a probability, right? Yeah, it sums to 1. And actually, if there are like anyone who likes mathematics and probability, actually you use the softmax function that is can be classified as a probability function according to the axioms of probability, but it's still the interpretation is actually not really useful. And you would like to interpret that this way. And so there are methods, for example, that I'll skip this one, but basically where you can, for example, define, for example, what's called an expected calibration error, meaning measuring the difference between this number and maybe the accuracy about dogs that may be 45. So you make the difference, and you can actually try to estimate, can I really interpret it as a probability or not. And you can see, for example, you can do what's called the reliability diagrams. For example, what you can see here on the right is you see the blue are actually the accuracy of a group of elements and then of observation, and the pink one is actually, it should be the probability, and this blue is the confidence, and this one is the accuracy. And you see that there is a difference, so it's difficult to interpret if you want to do any kind of scientific analysis, or say that, of all the dog, I really get 79% right. So this number tells me how imagine you have a group of stars, okay? You're classifying the stars. And for the stars, you get like 79 of this number, but in reality, you get only 45% right. So you cannot say that this number will tell you the ability of the model to classify that stuff type. Okay, and so you can do lots of like what's called model calibration. You see that, for example, if you see at the red curve is actually the expected calibration error, and the depth, it means it's an error network that is getting bigger and bigger and bigger, so more complex and more complex and more complex. And the more complex models are, the less are able to really do this properly. Okay? So the larger they are, this spits a number that actually has no real sense. So it's useful to get the results from an engineering point of view, but from an interpretation point of view are completely useless. And so it's, if you want to interpret that for some kind of hypothesis testing or so on, you have to be careful and do this. And there are like many ways, because if you really want to, so for example, there is like the temperature scaling. There are very easy way of bringing back this number together so that you can interpret that without touching actually the accuracy of the model. Okay. For example, temperature scaling is, this is actually a nice paper if you want to read about that. It's a nice introduction. And temperature scaling is nice because it doesn't change accuracy and it's easy to implement. But also, for example, you can temperature scaling. I think it's also already available in Python, so you don't have to interpret it to implement it yourself and so on and so forth. So it's relatively easy to use, but you have to know why, if you want to use it, and how to interpret the numbers and so on and so forth. Okay. Another, I've still like 15 minutes, right? 20 minutes, 15 minutes, right?
17.
17. Okay, so I'll go. So, for example, another point is that for example, something that I worked on is the following. Very often you give, when you have a model, if any of you have done any machine learning at all, like you measure, for example, in a regression task, you measure things like, for example, the mean square error, the mean absolute error, or the accuracy, right? But nobody think about the fact that, for example, if you're doing a regression problem, you're trying to predict the variable y, okay? The y will have a measurement error. If you're working in physics, you have a measurement error, right? So how this error propagates in the matrix. So you calculate an MSE, right? But your MSE or MA or mean absolute error are actually value without keeping into account that you have measurement error. So meaning that you assume that your data set is the perfect measurements, and that's not true, right? So if you, I'll just keep to, I'm sorry. Probably this one, sorry, I'll go back. So if you calculate how the error propagate, you'll see that, for example, the MSE, the top formula, for example, you have to sum the, for example, the standard deviation of the kind of the distribution of your y, what you're trying to predict. You may have cases, for example, the second one here, where, like, for example, you might have different groups of measurement with different error measurements. Right, so because that happens, you are maybe, you are measuring things that are like, I don't know, stars at different distances, and you have different errors, and so, and this is a much more reliable estimate of this matrix than simply the one from one data set. But this, of course, is larger. So if you're saying that your model is really good because we get that value, right? It may not be the case if you really consider that you have error measurements. And you have like also the formula for the variances, but that's more. But I think that already, like the first formula, it kind of gives I mean, from a mathematical point of view, it's a very nice formula because it's very intuitive. It's very intuitive. You have the MSE and you simply sum the sigma square, and it's really nice because it's you can understand how it works. For the absolute error, there is the absolute value, and it's ugly, because you have the absolute value, but you can calculate actually. And also for the accuracy, if you know, for example, for the accuracy, suppose that you're trying to classify stars, okay? And someone, you have like, you are doing supervised learning, meaning someone has given you the labels, right? Someone has classified it for you, and someone is saying this is star 1, 2, 3. Now, everyone makes mistakes, right? So, I mean, so you must assume that a certain percentage Q of your data labels are probably wrong. I mean, it's everyone. If you're labeling 5,000 stars, there will be mistakes. Now, Depending, maybe you have like, you've given this task to a young student because you don't have the time and the student doesn't really know exactly everything and there are border cases. And so you get 5% of errors. These 5% of errors will be reflected. So the real accuracy that you will get is actually not the one you get, but it's slightly less. Okay. And you have this portion here and you can actually estimate, assuming how much errors you have. Let me go back here, sorry. So another problem that you have is the following. When you, for example, when you do machine learning, again, you use mean square error and mean absolute error. But actually, the average values are not really useful, right? Because the problem is that not the average, the problem is what's the maximum error that you're going to do. Right? So if your model has a mean absolute error of 5 in some unit, but the maximum is 20, I mean, why should I care about the 5 if it can be 20? So if I have to say that I want to use my model for a set of new data and you have to give an error, you cannot give 5. You cannot give the average. You should give the maximum. You should take the worst case scenario and say, okay, the possible error is 20 because I cannot know if it's 5 or 20, if it's the maximum 20. So, and there are like, there is like a very beautiful theory in statistics that is called extreme value theory that allows you to study extreme values. So for example, the maximum of errors and how they're distributed. And so you can actually answer the question. I mean, it's a bit complicated, but you can answer the question, what is the probability that my machine learning model will make an error as large as something? Or you can actually reverse it and say, I'll give as a measurement error for, or let's say a machine learning error, I don't know, 95% quantile of this distribution value. Okay. And so you can actually say at 5%, I'll make 5% mistakes in my data set, but all the others will be below 20. I don't know, here is like some synthetic data set, I don't know, 22. Okay. So you can actually give a very precise kind of estimate. And so you can say, yeah, I know if I have 100 million stars I'm trying to analyze, and I know 5% will be, or you can say 1%, you can say the 99% quantile. Okay. So you can do these things, but the analysis is actually a lot more complicated than giving like, than doing the classical 80-20% split. You get an average that really doesn't tell you much. You can do cross, you can do Monte Carlo cross validation and so on, but it's still very, especially in physics, it's kind of useless giving the averages, for example. Okay. So this is what I showed you already. Then, okay, so another thing that is, it's lots of, it's actually very cool field in case you're working with differential equation and numerical simulations or physically informed neural networks. Now, to give you the context, is this, this is the kind of a spring with some friction, so and you have like a kind of a damped oscillator. At a certain point, it will stop. Or you should know how to solve the differential equation. It's not that difficult. But the question is, of course, like as any engineering, computer science probably think is that, what, it's not a problem. I'll just give some points and let the network try to learn it. But the problem is that the network learned what's happening when there are points. As soon as you are out of distribution, it's like, who knows, right? So it kind of do something, right? What you can do, actually, by using basically like the Lagrange multiplier approach, you can actually modify the models. I don't know how much you know, but usually you minimize the loss function in machine learning, right? You minimize kind of the error between like the expected and the input. And so you can put like equations that like the G there would be your differential equation. And you try and so this is how it would look like, right? So you have like a physics loss, you have the classical MSE, and you can use neural network because it's actually, you have what's called auto differentiation in software that allows you to actually calculate the gradients of very complicated neural networks. And you can solve actually those, this is actually minimizing the mean square error with the constraint that the physics loss is equal to 0. That's actually what we're trying to do. And when you do that, this is what you get, okay? So it works really well. So, and it's used a lot in fluid dynamics. in weather simulations, for example, when you have like those very complicated differential equations where you have like things like you have initial conditions, but you don't know actually how this will develop it out. Okay, and it's a really fun thing to do, but also here you need to know. I mean, to implement that is easy examples are easy, but then you need really to understand how the differentiation works. There is a bit of software engineering behind it, but it works really well. And so this is like, and it's today with the tools that we have via software, it's actually relatively easy to do. So it's actually so if you work with differential equations, you should look at it. The other thing that I was showing at the beginning is symbolic regression. I think that I know that some of you have never seen it, so it's actually very cool. Symbolic regression is also machine learning. Okay, so you have like data, and you give to the models, you give like the mathematical operators, sine, cosine, exponential, logarithms, plus, whatever you want, and then you actually, and of course constants and data. And you ask the model to find the simplest equation that approximate your data the best way possible. Okay, it uses genetic algorithms to search the space of possible equations, but it's actually very efficient. So just to make you another example, if you take the formula, it's a very dumb formula. Don't ask why this formula. But if you take this formula with two variables and y x2 is not there because it's a part of a larger example, but you generate randomly x3 and x0, you generate point, and then you actually ask it to generate, look, and you see here why I put this, because you see here the possible equations, right? And you get the score, and then according to a certain amount of criteria, not necessarily only the highest score, there are like other criteria like say complexity and so on. You get it chooses actually one equation, right? And you get like, and actually it finds the equation quite easily. Now, if your data is noise, it will not work as well, but it can really help. But sometimes when you do feature selection, sometimes it's like I did at the beginning, you realize if a variable is relevant because it doesn't need it to predict things. So that's also something that once you have the data, you might use it. For example, we're discussing with Tatiana, if you have like formulas that, for example, you have data points and you have approximate formulas that calculate that, you can actually check if there are corrections to the formula that might explain deviation from, not explain, sorry, that might, let's say, simulate those deviations, and then if you find out maybe what kind of terms, maybe gives you indication on what to look for in the formula or how to understand why there are deviations in certain ranges, for example. So that could be something that might be interesting. Again, noise will make things more difficult. So it's what I'm showing you is a very easy example, but when you go into the details, it's always like difficult. Yeah, and also something else that the very last point, what I would like to highlight is the following: when you're working with machine learning, there is in the past probably 2 to 3 years, there is what I call commoditization of the technology, in the sense that there are things that are easier to do, faster to do. And for example, if you work with Python, I guess most of you have, you go, there are scikit libraries, and you go there and you can do everything without implementing anything. So I mean, not from scratch, right? And that's a kind of a good side and a bad side. The good side is because it's very easy. The bad side is you don't think anymore why you're doing things. And so you have like lots of, so it's easy to do, but for example, we're discussing with Lorenzo about clustering. And at the end, very often what you have to do is you have to modify things in a way that you have to do it yourself anyway. And so, especially in scientific machine learning now, it's not that I'm saying that the master is not enough, or master students are not, or who has a master is not intelligent enough. It's not that. It's really like more to show that to really do scientific machine learning, it's a very sophisticated kind of way of doing machine learning that goes well beyond the engineering kind of approach where you simply, where you simply download and you use scikit-learn and implement it and you get the result and that's it. Okay. But for example, in computer vision, if you want to classify images, for example, you go on GitHub and you find that you can look at Ultralytics YOLO repository, and it's for free and it classifies everything really good. So if you really need just a piece in your pipeline to help you do something, for example, in computer vision, it's very easy now. So it's like you don't have to develop anything from scratch, convolutional neural network. You take something, there are instructions on how to use it for your images. The question is why you need to do that and how you put it into your scientific process. But there are like things like in computer vision, that are very easy to do. Statistics is a bit less. You have to understand it, and scientific machine learning, in my opinion, is really, it's not at the place where you can simply take it, download it, and use it. It's you have really to see how you use them. Yeah, so I had like other things, but basically that's what I wanted to show you. I have like 3 minutes, so 1 minute to spare, so it was brilliant time. Tatiana is against. No, it's okay. So maybe if there are questions, but what I wanted to do is just to show you a few things that may help you maybe in a project. So, but if you have any questions now, I'm happy to answer them.